Assalamu alaikum. Inshallah, we'll start today chapter 5, which is the application of the first law of thermodynamics for open system, or what we call actually control volume. Inshallah, in this chapter, as long as actually we have the mass equation in this case, we have mass transfer, so we have to apply the mass equation in this case in addition to the energy equation of the first law of thermodynamics. So inshallah, we'll develop the conservation of mass for the open system, and we'll apply actually this mass equation in case when we have a steady flow device, and also in case when we have also unsteady flow devices, or what we call actually unsteady flow in general. A steady flow, يا شباب, as you mean actually we don't have mass accumulation or energy accumulation within the system, and that's why actually the mass flow rate in case of a steady flow will equal to the mass flow rate out. And the energy dot in, the rate of energy input to the system, will equal to the rate of energy output. What is coming in is what is actually is leaving in case when we have a steady flow. In case of unsteady flow, in this case, like we have it charging or discharging a tank, filling a tank, or a tank actually is discharging. So in this case, in case of filling a tank, we have mass in, but we don't have mass out. So in this case, we have mass accumulation within the system. And in case actually of discharging a tank or leaking or something, so in this case we have mass out, but we don't have mass in this case. And in this case we have change of mass within the system with time. And this is called actually as unsteady flow. So inshallah we'll develop the mass equation and apply it for the case of steady flow and also for the case of unsteady flow. Then inshallah we'll apply the first law of thermodynamics for control volume. Control volume, يا شباب, means open system. The system allow actually for mass transfer. We call it control volume because the volume is fixed in this case. Unlike the case of closed system, we call it control mass as the mass actually is fixed. And in case of closed system, we don't have mass transfer, and that's why we don't have mass equation in this case. طيب, inshallah, we'll apply the first law of thermodynamics for open system. And as we said, as we have mass transfer, so we have energy transfer by mass. And we have to identify this term actually, energy transfer by mass. I think we have already identified this term in chapter 2. We said energy transfer by mass will equal to the mechanical energy of the fluid, which is the part of energy of the fluid that can be converted to work directly without having actually a device, plus actually the internal energy of the fluid, because this fluid has a temperature, so it should have internal energy. So the total energy transfer by mass will equal to the internal energy plus the mechanical energy of the fluid, which is actually kinetic energy, plus potential energy, plus the flow energy, which is BV. BV plus the internal voltage, the enthalpy. And based on this, actually, we have defined the term of energy transfer due to mass transfer is equal to the enthalpy of the fluid, which is internal energy plus flow energy, plus the kinetic energy plus the potential energy in this case. Inshallah, I will redefine this term again while developing actually the first law equation for open system. Inshallah, we'll talk about this term again, about actually all of the terms inside actually the first law equation. Then we'll develop actually the first law equation of thermodynamics for a steady flow open system. And we will consider actually apply this equation for some steady flow devices like nozzle, compressor, turbine, throttling valve. Throttling valve is a device that is used actually to reduce the pressure and the temperature actually of the flow in refrigeration system. We'll talk about this later on. Mixer, when we mix actually two fluid, like the shower, we mix hot fluid with a cold fluid. We'll talk about heater and also heat exchanger. When we cool down a hot fluid using a cold fluid, we call this as heat exchanger. And all of this actually, most of the engineering devices are actually steady flow devices. We don't have accumulation of mass within the system, and also we don't have accumulation of energy. They are steady flow devices. And inshallah, we'll consider all of these devices and apply the first law of thermodynamics for a steady flow open system. And then we will calculate actually, we will be able to calculate the work either input to the system or the work out of the system. And also we'll be able to calculate actually the heat transfer in the system by the application of the first law of thermodynamics. Also, we'll calculate the mass transfer by applying actually the mass equation, or what we call actually the conservation of mass principle. Then inshallah, all of our talk here up to this point, we are talking about a steady flow. Then we'll move to the case of unsteady flow. In case we are filling a tank, as I said, charging a tank or discharging a tank, this is unsteady process. Then inshallah we'll apply the first law of thermodynamics for unsteady process, and also in addition to actually the mass equation also for the case of unsteady flow. So inshallah in this chapter we'll be talking about steady and unsteady flow. But in all cases actually we have flow, okay? So in all cases we have flow. That means actually we have mass transfer in this case. And as we have mass transfer, then we have to apply the mass equation in this case, okay? Right, let's apply the mass equation. So the mass equation, or we call it actually as the conservation of mass principle. In this case, actually, very similar to the energy. If we have any system, let's say any thermodynamic system like this one, if we have mass input to this system, and part of this mass actually is leaving the system, and the remaining actually mass is stored within this system. So like energy, mass actually cannot be created or destroyed in this case. Unless actually for only one case, for the case actually using the Einstein equation, when we have actually a body that is moving actually with the speed of light or speed higher than the speed of light in this case. In this case, part of this mass can be just actually dissipated in the form actually of energy, in order actually to have this body moving with this actually very high speed in this case. And in this case, the conversion from mass to energy is equal to the mass multiplied by c squared. C actually is the speed of light. You can check here. The speed of light value is equal to about 3 multiplied by 10 to the power 8 meter per second. Okay, which is very high speed in this case. And if you have a body that is moving actually with the speed of light, in this case, part of the mass can be converted to energy in this case. Otherwise, actually, mass cannot be created or destroyed. So in this case, mass in will equal to mass out plus the part of mass stored within this system, like actually the case of energy. So mass in minus mass out will equal to the change of mass of the system. And this mass is calculated, this is the total mass calculated in kilogram. We can consider the rate form, so we can say actually m dot n, rate of mass in minus rate of mass out, will equal to dm by dt within the control volume in this case. Okay. So in case of a steady flow, we have the mass flow rate in should equal to actually the mass flow rate out, and in this case we don't have a change of mass within the system. Or d by dt, by definition of steady flow, d by dt should equal to 0. This term is 0 in case when we have a steady flow. Okay. So in case for a steady flow, when we have actually steady flow open system, then in this case actually we can say rate of mass flow rate in will equal to the rate of mass flow rate out. The mass flow rate in will equal to the mass flow rate out, and we don't have any accumulation of mass within the system. But if we have system, let's say we have more than one inlet. Let's say we have mass inlet 1, rate of flow rate mass inlet at another cross section 2, and here actually we have more than one outlet in this case. In this case, if we have more than one inlet, more than one outlet, so in this case we have to add the summation sign. So the summation of all of mass flow rate in should equal to the summation of all of mass flow rate out in case when we have a steady flow in this case. Okay. But if we have single stream, that means we have only one inlet, and only for this system we have also one outlet in this case. So in this case we can remove the summation. So for single stream, so when we have a single stream, just only we have one inlet and one outlet, then we can remove the summation sign. So it will be mass flow rate in will equal to mass flow rate out, or m dot inlet will equal to the mass flow rate actually m dot exit. And the rate of mass flow rate is actually calculated in kilogram per second. Okay. Like how we can calculate the mass flow rate? This is something very basic. So mass flow rate actually is the rate of mass, or mass per unit time, and the mass is equal to the density by the volume. So let's say we have a flow. This flow actually is going inside a tube. Okay, this flow inside this tube is moving actually with a velocity v. If you look at the distribution of the velocity within a tube or within a pipe, it would be something like this. In this case, the velocity will be maximum at the center of this tube, velocity of the flow. And actually, this value of the velocity at the interaction with the wall, due to the no-slip condition, the velocity here actually should be equal to 0. Okay? So the velocity of the flow flowing inside the pipe, it's a kind of parabolic distribution at any cross-section. This will be the distribution of the velocity of the flow. The velocity should be maximum at the center line of the tube because we don't have friction. The friction is minimum at this point, and the velocity due to the no-slip condition at the wall will equal to 0 in this case. So if I need to calculate the velocity, sorry, the mass flow rate. So in this case, I have to calculate the value of the average velocity, V average in this case, okay? To calculate actually this velocity, as you can see, is function of the radius, okay? So to calculate a very accurate value of the average velocity, so the velocity V average by definition is equal to 1 over the cross-sectional area. This is the cross-sectional area of this section at any section. Integration of the velocity as function of the radius, as you can see, velocity is function of the radius of the tube. So we should have this function. It's a kind of parabolic function, integration delta area. Okay? Delta area for a tube, if it is actually tubular cross-section, delta area is equal to pi r squared. So differentiating delta area, it will be equal to 2 pi r dr in this case. And then we can just substitute here integration dr from 0 to the radius of the tube r. The radius actually is the outer radius here. Let's say it r capital. So from 0 to r capital, we can calculate the average velocity in this case. But in your problem or in application, in this case, the value of the average velocity will be given directly to you. So in this case, to calculate the mass flow rate through this system, we have the mass is defined actually as the density multiplied by the volume. So by definition, density is mass over volume. So mass is equal to density multiplied by the volume in this case. And mass flow rate, we have to define it actually by time. So instead of volume flow rate, we call it actually the volumetric flow rate in this case. And this volumetric flow rate is calculated in meter cube per second. Or mass flow rate is equal to the volumetric flow rate. This density is equal to 1 over a specific volume, as you know. So it will equal to the volumetric flow rate divided by the specific volume. And this mass flow rate is calculated in kilogram per second. Okay? And this volumetric flow rate is equal to what? The volumetric flow rate is equal to the cross-sectional area multiplied by the average velocity in this case. The value of the average velocity should be given for you. So the mass will equal to density multiplied by the volumetric flow rate, which is area multiplied by the velocity in this case. And this is how we define the mass flow rate. Area is the cross-sectional area, and this velocity, shabab, is the velocity that is normal to the cross-sectional area. It is the component of the velocity normal to the cross-sectional area, in this case. Okay? Type, if we have incompressible flow, what does it mean, incompressible flow? Incompressible mean actually this fluid actually does not affect much. The properties does not affect much by the pressure, and that means actually for incompressible flow, the density will be constant in this case, as we have learned. Incompressible flow, in case of incompressible flow, the density should be actually unchanged or constant in this case. We said incompressible substance like solid or liquid, but here we are talking about flow, so we don't have flow of solid. So we are talking about liquids in this case. So if we have flow of liquid substance, like liquid water, so that means the density is constant in this case. But if we apply the mass equation, like the flow in this duct, this flow actually is coming to this duct at cross-section 1 and leaving at cross-section number 2. So this is a steady flow device. So in this case, we have single flow stream. So we don't have the summation sign. So m dot inlet will equal to m dot exit in this case. We call this a section. Inlet is equal to section 1, and outlet actually is section 2. So we can say m.1 is the same as m.2, or we can say density ρ1 multiplied by area A1 multiplied by the velocity V1 will equal to ρ2 multiplied by the exit area, which is area 2 multiplied by the velocity V2 in this case. But in case if we have incompressible substance, density is constant, so that means density ρ1 is the same as ρ2. So in this case, we can say actually the velocity V1 multiplied by the area A1 will equal to the velocity V2 multiplied by the area A2. And the velocity by area, which is the volumetric, actually we call it the volumetric flow rate. So in this case, the volumetric flow rate in this case is also constant. The volumetric flow rate at the inlet section is the same as the volumetric flow rate at the outlet section in this case. Similar to the mass flow rate at the inlet section is the same as mass flow rate at the outlet. But we cannot say actually for incompressible substance that this is actually, we cannot say actually this is a conservative actually, or the volumetric flow rate is conservative in this case. We don't have conservation of volumetric flow rate. We have conservation of mass. Mass is conservative, cannot be created or destroyed. But we have a special case for incompressible flow. In this case, density is constant, so we can say also the volumetric flow rate that fixed from the inlet to the outlet section. But we cannot say we have conservation of volumetric flow rate. No. We have only conservation of mass. A special case when we have an incompressible flow, then we can say the volumetric flow rate will be fixed from the inlet to the outlet section. You can look here, Shabab. Here is what I'm saying. I will get back to all of this. So in case of incompressible substance, the volumetric flow rate at the inlet, area 1 V1 will be the same as the outlet, area 2 V2. But in this case, there is nothing called actually the conservation of the volumetric flow rate. We have only conservation of mass in this case. Okay. But special case, as we said, in case when we have liquid, density will be constant. So in this case, actually, for incompressible substance, the volumetric flow rate will be remaining constant. But in case of compressible flow, like gases, incompressible liquid, but compressible in case of gas, like when we have a compressor takes the air, and its function is to raise its pressure. So in this case, the density for gases, density is equal to what, Shabab? Density for gases is equal to B divided by RT, as we have BV is equal to RT. BV, specific volume, is 1 over density. So density will equal to pressure divided by RT. The function of the compressor is to raise the pressure. We have input mechanical energy to move the shaft, then we can actually raise the pressure of the flow. Okay? Type compressor is a steady flow device. A steady flow device, that means the mass flow rate at the inlet section, which is in this example is 2 kg per second, should be the same as mass flow rate at the outlet. We call it actually the conservation of mass. But in case of compressible, this is gas, that is mean actually it is compressible. Density is not constant. Density is function of the pressure in this case, which is low at the inlet section and high at the outlet section. So the volumetric flow rate is equal to the area multiplied by the velocity. The volumetric flow rate at inlet is equal to 1.4 meter cube per second, and at outlet the volumetric flow rate has been reduced. Why the volumetric flow rate has been reduced? Because the mass flow rate actually is the same. At inlet is the same as outlet, and this is the volumetric flow rate. Here actually this term, the density multiplied by the volumetric flow rate at inlet, is the same as density multiplied by volumetric flow rate at outlet. But the density at the outlet section has been raised. That means actually to keep the mass flow rate constant, this term, the volumetric flow rate area by velocity, should be reduced in this case. And this is actually in the case of compressible flow. Compressible, that means actually the density is not constant. What is conserved actually is the mass. And we cannot say we have conservation of volume in this case. Okay, this is what we said. This is the conservation of mass. So this equation, Shabab, that we have developed for mass, we call it actually the integral form of the mass equation, which is mass in minus mass out, or mass flow rate in minus mass flow rate out, is equal to the rate of change of mass within the control volume. This form of mass equation is actually the integral form of the mass equation. We can also develop this integral form of mass equation from the differential form. We can also develop the integral equation from the differential form of the mass equation. So let's consider differential form of mass equation. Okay, differential form means we have to have an element, take an element and do the integration. Then in this case we can get the integral form to calculate the mass transfer within a system. But let's consider actually an open system. This is an open system. We call actually the area inside this system as the control volume, and the surface actually of this control volume, we call it as the control surface. So in this case, if we have mass input to this system, and we have mass out of this system, and part of mass actually is stored within this system, then if we apply the mass equation or write it actually in the integral form, so it will be mass in minus mass out will equal to what? Mass within the system or within the control volume in this case. Okay, or we can write down actually in the rate form, rate of mass in minus rate of mass out will equal to dm by dt within the control volume or within this system. Okay, this term we should have is mass in minus mass out, which is the mass either into the system or leaving the system. This mass into the system or leaving the system should cross actually the control surface of this system. So this is actually the mass that is actually crossing the control surface of this system. But what about this term dm by dt? This is actually the change of mass within the control volume itself. So this is the change of mass within the control volume or within the system itself or inside the system. Okay, type this form we call this actually as the integral form. This is the integral form of the mass equation. And how we can develop this integral form from the differential form, or how we can actually develop the differential form? Developing the differential form, that means we have, this is actually a system, open system. We have to take an element and then we can do the integration. Then from this differential form, we can get actually the integral form. But let's do so. Let's say this is actually the control surface. We can just consider an element from this actually the area of the control surface. We can take a small element or infinitesimal element. This element actually has area vector normal to this element. So n is the direction of the area, and let's say we have actually flow that is leaving this system with a velocity v. This velocity actually is leaving with a direction vector that has an angle theta with the area, the n vector, which is normal to the cross-sectional area in this case. So if we look at this element and look at actually the masses either coming in or leaving actually the system through this element, and then we can do the integration to get this form. But what about, let's say, actually consider the first term, mass flow rate n minus mass flow rate out. If we have mass in or mass out of this system, it should cross actually the control surface in this case. And this mass should equal to the total mass. It will equal to integration of the mass leaving actually this element. So the mass of this element is equal to what? Is equal to the density multiplied by what? Multiplied by the area, multiplied by the velocity. And we said this velocity is the velocity that is normal to the area. Or actually it is equal to the area multiplied by velocity cosine theta. Or velocity cosine theta, we can say actually it is the dot product of velocity multiplied by delta area. So we said this integration, this flow either can be into the system or leaving the system. So in this case, we can do this integration from the inlet to the outlet of the system and crossing the control surface of the system. If we do this integration, it will be the density multiplied by the velocity, the component of the velocity multiplied by component of the velocity in the area direction multiplied by the area at the outlet section, minus actually the mass flow rate at the inlet section, which is the density multiplied by velocity multiplied by area. But if I did this integration, it will equal to what? it will equal to mass flow rate out minus mass flow rate in. But here we need to calculate what? Mass in minus mass out. So in this case, we have to have a negative sign here. Okay? But this is regarding actually this term, mass flow rate in minus mass flow rate out. So what about the second term? Second term actually is the change of mass within the control volume itself. Okay? By definition, we have mass is equal to density multiplied by volume. Or we can say the change of mass differentiation, it will equal to density multiplied by delta V. And let's look at the second term, dm by dt within the control volume. That should equal to d by dt. dm, this is actually the mass. Mass is equal to integration of, so if we integrate here, so the mass will equal to integration of dm, which is integration of rho dv. So mass here is equal to integration over the control volume of dm, or it is equal to d by dt, integration over the control volume dm, which is rho dv in this case. Okay, and this is actually the differential form of the second term of the integral form dm by dt. So this is actually the first, the right-hand side term, and this is the left-hand side term. So we can substitute mass in, mass flow rate in minus mass flow rate out. This term can be substituted by this term, by this integration, and this term actually can be also substituted using actually this form. So let's do this, substitute. Then we can get the differential form of the mass equation. So this is something for your knowledge. To get the differential form, I have to take an element, and then we have to do the integration through this element to calculate the total mass flow rate through the system. So the first term, mass flow rate in minus mass flow rate out, that should equal to minus integration over the control surface from the inlet to the outlet, rho multiplied by velocity multiplied by delta area. This term, this is actually representing mass flow rate in minus mass flow rate out. That should equal to d by dm by dt, which is equal to d by dt integration of rho dv. This integration is through the control volume. We say that this term is the change of mass within the control volume itself. And this term actually is the mass crossing the system, either in or out, and it should be crossing actually the control surface of the system. Okay? But let's do this integration, Shabab. So this negative sign, we can take the whole term to the other side. So in this case, we will have integration over the control surface from the inlet to outlet, rho multiplied by velocity delta area, plus d by dt integration over the control volume rho dv. That should equal to 0. And this is actually the differential form of the mass equation. From this differential form, if we do the integration, we can just get actually the integral form. Okay. I'm just going up through actually those proofs or something just to know actually the link between the differential and the integral form. But actually, when it comes to the application, we'll apply directly the integral form. Okay. But let's do this integration, so it will be what? Integration from the, so it will equal to mass flow rate outlet. It will equal to rho exit multiplied by V exit multiplied by area exit. And we said this velocity is the velocity that is normal to the cross-sectional area, the component of the velocity in the area direction, which is in the direction of the vector n, okay, which is the area vector. Time. This is actually at the exit, minus at the inlet, it will be rho inlet, velocity V inlet multiplied by area inlet in this case. And that we can take this term to the other side, will equal to minus d by dt integration of rho dv. This integration is over the control volume. Okay. But if we have more than one inlet or more than one outlet, then in this case we have to add the summation sum. The summation of all mass flow rate leaving the system minus summation of all mass flow rate coming into the system is equal to minus d by dt integration of rho dv. Type we see this term d by dt, this term will equal to 0 in case when we have a steady flow. Then again, I will get back actually to the form I have written before. So for a steady flow, and that you have to keep in mind, in this case, we have summation of M dot exit will equal to summation of M dot inlet if we have more than one exit or more than one inlet in this case. Or we can say summation of row exit, V exit, area exit will equal to summation of row inlet, V inlet multiplied by area inlet in this case. Okay? In case of single stream, I will repeat this again. In case of single stream, we have only one inlet and one outlet. So in this case, M dot inlet will equal to the same as actually M dot exit, or we can say row inlet, V inlet, area inlet will be the same as the exit section. Okay, density multiplied by area multiplied by velocity at the inlet will equal to the same as the outlet in this case. In case when we have single stream in this case. But in case of incompressible substance, in this case the density will be constant as we said, and in this case area multiplied by at the inlet should equal to the same as area multiplied by velocity at the outlet section. And here yani is a situation. Okay, this is what we said. And let's yani look at this example. Okay. Here is an example to apply the mass equation. So يا شباب, for a steady flow, if we have a steady flow, this is the main subject actually of this chapter. In this case, the mass equation, either from integral or differential form, it will be reduced actually to the summation of mass flow rate inlet is equal to the summation of mass flow rate. Summation of mass flow rate outlet is the same as summation of mass flow rate inlet in this case. Or we can say the summation of density by area by velocity at the exit section is the same as density by velocity by area at the inlet section. In case when we have a system of single stream, we have single inlet and single outlet, then in this case we can say M dot inlet will be the same as M dot outlet for a steady flow, or we can say density by velocity by area at the inlet will be the same as at the outlet section. So this is actually what we need out of the mass equation in case when we have steady flow. Okay. But let's have an example here. Let's look at this example. Here he said we have a hair dryer. The hair dryer, شباب, its idea, we have a duct of constant cross-sectional area. This duct actually is the air dryer. We have a fan. So this fan takes the air. So we have air here. It's coming the atmospheric air, coming with actually the normal atmospheric temperature or normal pressure. This fan actually is connected to an electric motor, and that's why we connect the hair dryer to the electric to drive the electric motor. Then we can drive this fan. The fan will be forcing the air to go through an electric heating coil. So we have electrical work input in this case. So this electric heating coil, as you know, is high resistance coil. So when the current is passed through the system, this electrical energy will be converted to heat. And this heat will be absorbed actually by the air. And at the exit actually of the air dryer, in this case, we will have hot air in this case. Okay. Type in this problem, he said the density at the inlet section. He said the inlet section is, let's say, 1, and the outlet section we call it as 2. He said the density at the inlet section of the air coming in is equal to 1.2 kilogram per meter cube. And the density here at the outlet section is equal to 1.05 kilogram per meter cube. Okay, and we need to calculate actually the percentage increase of the velocity within this air dryer. Okay. So this air dryer, شباب, is steady flow device or unsteady flow device. So unsteady is only special case when we have like a tank that we are filling or a tank that is discharging. Otherwise, it is a steady flow. And most of the engineering devices are steady flow devices. So in this case, the hair dryer, does it accumulate mass inside? No, it is a steady flow device. The mass flow rate in is the same as mass flow rate out. But do we have more than one inlet or more than one outlet? No, this is a single stream. So in this case, applying the mass equation, for a steady flow single stream, then in this case we can say mass flow rate inlet to mass flow rate outlet, or omega dot exit will equal to m dot inlet in this case. Or we can say instead of inlet and outlet, we can call it as 1 and 2. Then we can say rho 1 A1 V1 will be the same as rho 2 A2 multiplied by the velocity V2. Up here, actually, this is a cross-sectional, constant cross-sectional duct. So this is the area of the duct is constant in this case. So we have the area A1 is the same as the area A2. This is actually a constant cross-sectional area duct. So we can calculate from here the ratio between the velocity V2 and V1 will be the same as the density of the ratio of the density. So velocity V2 over V1 will equal to what? Rho 1 divided by rho 2, which is equal to 1.2 divided 1.08 will equal to 1.14. So the percentage is equal to what? Percentage increase in the velocity will equal to what? V2 minus V1 with respect to V1. So that, and this is multiplied by 100. That should equal to V2 divided by V1 minus V1 over V1, which is 1 in this case, multiplied by 100. Okay? So V2 over V1 is 1.14 minus 1, so it will be 0.14 multiplied by 100, so it will equal to 14%. Okay? This is the details of it, but when you look here, V2 is over V1 is 1.14, that means we have 14% increase in the velocity in this case. Okay, and that's all Shabab regarding the mass equation. We have to move here to the next part of this chapter, which is the energy equation, which is the main part in this case. But as we said, as we have mass transfer in case of open systems, then in this case, energy can transfer by heat, energy can transfer also by work, and also energy can transfer by mass transfer in this case. I told you we have already defined this term, energy transfer by mass. We said energy transfer by mass if we have, let's say, a flow inside a tube or something. We said the term of energy transfer by mass is equal to the mechanical energy of the fluid plus the internal energy, because this flow should have actually a temperature, so it should have an internal energy. The mechanical energy of the fluid, as we defined in chapter 2, is equal to the kinetic energy, which is half V squared, plus the potential energy, which is Gz, plus the flow energy due to pressure, because the flow will not be moving unless actually the pressure is high. Pressure P1 is higher than the pressure at any downstream point in this case. So we have flow energy, which is PV. And we have defined this term actually in detail in chapter 2. This is actually the mechanical energy of the fluid, which is the part of energy of the fluid that can be directly converted to work. We call it the mechanical energy. Plus the part related actually to the temperature or the internal energy. Plus, in this case, we have to add U in this case. We said U plus PV, this term actually is representing the enthalpy. And in this case, the energy transfer, the specific energy transfer by mass, which we give it the symbol theta, will equal to actually internal energy plus flow energy, which is enthalpy, plus kinetic energy, which is half V squared, plus potential energy, which is equal to G multiplied by gravitational acceleration. Or we can say the total energy transfer due to mass transfer. This term will equal to mass multiplied by the specific energy, which is theta. So it will equal to mass multiplied by enthalpy plus kinetic energy plus the potential energy in this case. And also we can write down the rate of energy transfer by mass, E dot. We have to divide in this case by time. So when we divide by time, so divide the mass by time, it will be the mass flow. So the rate of energy transfer due to mass transfer will equal to m dot multiplied by theta, it will equal to m dot multiplied by the enthalpy of the fluid, plus the kinetic energy, plus the potential energy. And this is the term of energy transfer by mass. We said energy for any system, open system. Energy can transfer in or out in the form of work. Energy can transfer in the form of heat. And energy also can transfer either in or out due to the mass transfer in this case. Okay, and this is the term rate of energy transfer by mass in or out of this system will equal to the mass flow rate either in or out multiplied by the enthalpy of this fluid multiplied by the kinetic energy plus the kinetic energy plus the potential energy in this case. Inshallah, next time we'll take all of this term and then we'll apply the first to develop the first law of thermodynamic equation for a steady flow, and then inshallah later on we can develop this equation for the case of unsteady flow. I think we have developed the equation already for a steady flow in chapter 2, so inshallah we'll be just revising it. Assalamu alaikum.